Oh man. A lot of coffee. Rafael got it.
This is really good coffee. All right. What else, guys? Let's see. All right, so density relationship. All right, so how will changing KVP affect beam quality and quantity? All right, well, let's take a look. Increasing KVP increases the beam penetrability, right? And so what this is saying is that you're gonna have more photons reaching the image receptor. Yes? If you have a more powerful beam, okay, if you have a bigger punch, that's what it means, right? In addition, it will increase beam quantity because of the reasons that that Amanda explained. But can you repeat that, Kayla? Yeah, let's make sure that we get it. This part here, in addition to increase the beam quantity. What does this say? Careful there. Okay, I want you to explain this part, the second part. In addition, it increases beam quantity. Why increasing the KVP increases the beam quantity? What type of, where are those interactions? Where? What's going on? Take us one step at a time. Because you do have more interactions at one point, but you have less at another point. So I just want to make sure where. What do you think?
You have more interaction inside the tube, creating photons, but then you're creating less scatter in the patient, but the scatter is more high energy, so it's able to reach the image.
Okay, all right. Okay, so you explain more. Good, that's fine. But this is explained because the interactions that you have within the X-ray tube, like you said, in the anode, right? Yeah, everybody? Okay, that's what happens. So thank you. So either of you, I ask you in a month, you'll remember.
Sure.
All right. Decreasing KVP will be the total opposite. Okay, what happened there? So I'm not gonna explain. All right. How many of you have heard about the 15% rule? A few of you. Okay. All right. So I'll go over it. Okay. This is a rule that doesn't really have an application in computerized systems. In the computerized system world, not really. Not really. Okay. This was a rule, and it was not even a very good rule. It was a really flaky rule, okay? But it was still, it had some application with film. That application, you don't have it with computerized systems, right? So, for your technologists have been saying, okay, the 15% rule, we're gonna apply. Maybe they're a little bit confused, okay? So, how it is? Okay, let me explain it. Because KVP affect both quality and quantity, a change of only 15% will demonstrate a doubling of the film density, underlying film and underlying density. What did I say about computerized systems and density? Huh? We changed this to exposure, okay? All right, but not to density. Now, in this case, before you start adding stuff, in this case, for the 15% rule, don't change it to exposure. Okay, because it's not gonna work. It doesn't work. All right, because you're not doubling the exposure. Okay. All right. So let me explain. So what happens here with the 15% rule? So let's get it out of the way. The 15% rule works. Let me start with this. Let me start by saying this. The 15% rule works if you are between, and these are an approximate range. If your KVP is approximately between, I mean it's approximately, right? 70 KVP all the way up to about 85, 83, somewhere around there. So what this rule said, okay, was that if you were, and by the way, this is from my own experience, guys. There is no textbooks, there is no, people have tried to come up with definite numbers, and it's almost impossible because, as I said before, it's a flaky rule, okay? But for the most part, if you are within this range, the rule did apply, did work. And so what was saying, the 15% rule said that if you increase your KVP by 15% at any level here, you double the density, okay? If you're using radiographic film. For example, if you, I don't know, you were doing a portable and you were doing a hip, okay? Came out light, okay? And you wanted to double the density. You had two choices, either double the mass or go up 15% in KVP, okay? And then the image came up with double the density. Okay. Now, this doesn't apply to computerized systems because when you increase KVP, you're increasing the penetrability and you increase the quantity. You increase two things. And computerized systems don't work that way. Okay? You might increase your KVP 15%. Your image might look exactly the same as the previous one. Okay? There are other factors. So the 15% rule, it doesn't hold with computerized systems. Okay? Now, what happened, and I'm not going to spend too much time on it, but I'll explain a few more things. What happens if you are below 60 or below 70? Say you are at 60 kVp, or let's say if you are at 100 kVp. The 15% rule doesn't work. Okay, doesn't work at all. If you are at around 50, 60, then you need to, your 15% rule change to the 7% rule. All right, so all you needed got my secrets. All colors. Yeah. All right. What color do we need? We need red. Red. Cool. Brown too. Brown. Light blue. So the 15% rule really turns to about the 7% rule, which was never a rule, but I'm calling it. That's all you needed to change, about 7%. When you were at about 100 and above, or 90 and above, yeah, let's say 90 and above. Okay, and then that change became more like a 30% rule. Okay. Once again, I don't think I'm not going to ask you about the 15%. Well, I'll ask you just the general idea of the 15% rule, but I'm not going to ask you to do calculations and all of that. No, because it doesn't, you might not even see it. Okay? Any questions about this? Yunji? All right. No. All right, good. So that's it. That's the 15% rule. All right, now let's go to distance. This is important. All right. So as the source to image distance increases, beam intensity will decrease. That makes sense, right? If you're moving farther away, so say think of this projector. If you move it to the end of the room, the intensity here is going to be a lot less, right? But with a flashlight, you turn on a flashlight and you keep moving farther and farther away, the intensity is less. Same thing happens with X-rays. The farther you move, the less intensity you have. Okay? And remember, intensity refers to? Intensity refers to? She said, quantity. Intensity in diagnostic radiography refers to quantity. Okay? So, not to the energy. All right, so, and vice versa. What it's saying is that if you bring the point source, you bring it closer, then the intensity will go up. The amount of X-rays will go up, right? Yeah. If I move my hand closer to the projector, the light that is striking my hand is going to be more and more photons. It's going to look brighter, right? Okay. So this takes us to the inverse square law, right? That we already studied. Right? So let's take a look at it again. So the intensity of the radiation at a given distance from a point source is inversely related to the square of the distance between the object and the source. Okay? So basically, in simple terms, what this is saying, if you double your distance, okay? If I move away, if I double the distance from the source, then the intensity will go down by 4. And vice versa. If I halve my distance, okay, then the intensity will go up by 4. Okay? If you don't have a specific, or if you don't have, if you're not doubling or halving, then just apply the formula, right? Formula right there. Well, not that one. What is the inverse square law formula? Only one person at a time, so you start it. So you go ahead.
I1 over I2 equals d squared 2.
You what?
D squared 2 over d squared 1.
Okay. All right. Everybody agree with that? Okay. So now, this is called the Magnus formula, or the mass formula. And this one has a nice application to X-ray technology and technique formulation, okay? Because if you change your distance, okay, you can come up with a mass, changes in mass, and it works, guys, okay? It works. I will put my hands on fire. This thing is true, okay? This thing is true. It works, okay? When you apply it properly, it will work. And if all the other factors remain the same, it will work, okay? All right, so what this is saying, and remember, what's the only difference that you see, Dennis, what's the difference you see with the inverse squared law here?
It's
Intensity 1 over intensity 2, I'll help you with that.
Yeah.
What else?
Reverse?
And so, Gracie?
So it's proportional to.
And so what does it mean by proportional? Tell me what type of change we'll make here. D2 on top, D2 on the numerator, D1 on the denominator, right? If you're doing the inverse square law,
Oh, yeah.
Yeah.
that's what I'm saying. So what's the
Okay.
difference between the two? All you're gonna change is just that.
Yeah.
All right. All right. Come on, guys. We need to energize you here. Provides technique correction for changes in SID. So it has an applicable interest to us, to X-ray techs. Okay. With that, I'm not saying that the inverse squared law is not important. The inverse squared law is very important, especially when it comes to radiation protection. Very important. Okay, that you maximize your distance from the source, right? Okay, good. So you don't want to be right next to the X-ray tube, and you don't want to be right next to the patient when you are doing that exposure, right? Sure. So fall asleep with me if we're falling asleep. All right, Mona, are we good? Feeling strong? Okay, come on, just hang in there. All right. We have to go over this stuff, guys, otherwise I will let you go. So we have to. All right, give me good 10 minutes and then you go, all right? All right, give me good 10 minutes. All right, can you do that? Good. Okay, you see sparky eyes, right, Mary? Okay. Kayla, I want you to stop doing whatever you're doing. Ms. Vasquez, don't do that. Give me good 10 minutes. Good 10 minutes. Okay. Oh, she's taking good notes? Okay, good. Give me good 10 minutes and then you go. All right, here we go. Whew. All right. Distance and its effect on him. Yeah, there you go.
Yeah.
So 10 minutes. Okay, so all right. Here we go. So distance and its effect on image receptor exposure. So you can see here, Another thing, remember, when you change your distance, you're changing the geometry of your system. And so that will affect what? Resolution. Resolution. Okay? And see this little gadget here? Okay, this is a little test tool that is used to, you have line pairs per millimeter. You don't see it very well, but you have lines, the number of lines here, the number of millimeters here. So you squeeze these lines, and the more lines you can see, the better the resolution of that system. Okay? All right, good. Okay, standard SID, stable top, 40, right? 40 is almost equivalent to 100 centimeters. If you want to be a perfectionist, it's actually what? 90, what is it? About 98.6, something like that, okay? But roughly 100 centimeters, okay? I guess we can apply common core now. If it is close enough, that's good.
How do you feel about Common Core?
Common Core. I get headaches about common core. Chest radiography and other selected exams, okay? 72, approximately 180 centimeters. Okay? All right. Are we good? All right. Density and contrast control through post-processing too, okay? Especially with digital systems. So it is the algorithms that you use, the formulas that you use, and how they are applied. That's really what gives you the density. Remember that you might underexpose the patient by 50%, and the densities is still fine. You're gonna have quantum model, but the density, the overall density of the image looks the same, okay? You can overexpose the patient 300%, 200%, and the system will make it work, okay? The density will look fine, but the patient was overexposed. But it's just the system that it makes it work, okay? Still, the image receptor must receive proper exposure. Otherwise, it's not gonna work very well, okay? If you underexpose it, quantum model is a problem. If you overexpose the patient, or if you overexpose the detector, then what you have is you start getting very gray images. The system doesn't understand, it's overloaded with information, and so you have to be close to the range of exposures you can use. All right. Digital image receptor systems, KVP, based on desired contrast. So KVPs only change when you don't have the right contrast, and add here, please, when you want more or less penetrability. Remember the other day I gave you the example with the chest X-ray, and I said if you don't see if you don't see the spine, if you don't see a little bit of the thoracic spine, it's probably underexposed. If you see too much, it's overexposed. So also when you're looking at how much penetrability you have. So that's the only time where you change KVP. Distance selected based on the SAR beam geometry. Okay, what is it that you want to do? How much you want to change the resolution of the system? Okay, mass is adjusted to meet exposure needs. Okay, that's the only time where you want it. Okay. All right. Okay, that was it. That was a quick review. All right. Okay, give me another 5 minutes. Okay, 5 minutes have passed. Give me another 5 good minutes, and then we'll move on. All right. All right, so here we go. This section is just pure radiographic quality. Right, Mona?
Yeah.
Yeah, look at her. She's good. All the smiles now, and yeah, we're ready. Okay, so let's see. It is the exactness. Okay? When we think of radiographic quality, we always think of density, we think of contrast, we think of resolution, but how do we define it? And this is one of many designations we can use. All right, so radiographic quality can be defined as, it is the exactness of representation. Exactness, what do I mean by exactness? Anybody? Exactly, the most accurate. You know, a good copy of the original, right? So that's what I'm saying. It is a good copy of the real anatomy, okay, on a radiograph with the useful density range. Okay? So a good quality radiograph is one where you're gonna have the anatomy you're trying to represent is gonna look very similar. Yes, Kayla?
When you say radiographic quality, are you talking about
I'm talking about all of the above.
good or bad?
Is a good representation of the anatomy. And that includes good density, or adequate density, adequate contrast, and adequate resolution.
Okay, so it's not referring to.
It does, that's part of it. Okay? It's part of it.
So this is deciding if the image is good or bad?
Yes, that's what you're gonna decide. So when you're doing your image analysis and your clinical coordinator asks you, what do you think of this radiograph? Well, you say, well, I think the quality is good. And then you say, why is it good? It is good because it has good density, it's good because it has good contrast, and the resolution is very good. Then you say, oh, that's good. Right? That's good quality. A bad quality radiograph could be one that is lacking density. Okay? It could be one that is lacking penetrability. Could be one that has poor contrast. Or you don't see any resolution. All of it will make it a bad image. And the opposite is true if it is a good image. Yes?
Is density brightness?
Say that again?
Is density brightness?
Brightness. That's the term that is used in computerized systems. Brightness. Now, the controlling factors of density are not the same controlling factors of brightness. Okay, so remember that. Okay? All right. Because the brightness is controlled, and the computerized system is controlled by the algorithms. All right, radiographic quality. A high quality radiograph is one that demonstrates a specific anatomic part, okay, interest with a sharp image. That's, okay, sharp image meaning that good resolution, right? And with the appropriate density. And that's, what's density? That's the darkness of the image, right? And what is contrast? The difference in those darkness that you see in the radiograph. The image must have at least the least amount of magnification and distortion, which affect resolution, of the actual size of the shape of the anatomical part. Okay? So, for example, if you're trying, this becomes a little tricky because if you're trying to, you guys are doing the skull, for example, it's difficult to represent that because you're going to have distortion no matter what you do. Because this is a three-dimensional structure and now you're trying to represent it on a one-dimensional type of image. Okay? All right, good. So, factors that affect quality. Now that you know what good quality is, these are the factors. We'll go back again to the same things. Density, contrast, density, or what's the other term that we use? Density? Brightness. Okay, one more minute, guys. We're almost here. Distortion. Okay, so let's take a look. So now we're going exclusively with density. Let's stop here. All right. Good. Good job. Huh?